thing on Earth, whether it's me, whether it's you, whether it's a tree, whether it's a bacterium, even things that aren't really living like viruses, they all have a genome. They have this very simple instruction book written in 4 letters that says, this is how you make a living thing. And just like we can read a book, we can read genomes too. And it turns out that, just like books in the world are all sort of subtly different from each other, genomes out there are subtly different from each other. One version, one edition of a book might be slightly different from the previous edition. We can look for those tiny changes and use them to describe the relationships between bacteria, between viruses. How I like to explain my work is using the analogy of the kids' game telephone. So in the telephone game, kids will be sat in a line, somebody will whisper a sentence to the first kid, they whisper it to the next kid, who whispers it to the next, to the next, to the next, to the next. Sentence reaches the end of the line, kid at the end says what they heard, person who whispered the sentence to the first kid in the line says what they inoculated that line with, and everybody laughs because it's different. The sentence has mutated as it spread from kid to kid to kid. The same thing is happening with a pathogen's genome as it spreads from person to person, moves forward through time in an outbreak. So what we're doing with our work is really just reading the genome of each of those pathogens. We're sort of asking the kids, what sentence did you hear? What did you hear? What did you hear? And we're saying, okay, well, in what order were those kids sitting in? The order that a change, arises in and is passed down to kids further down the line, we can use that information to figure out exactly the order they were sitting in. We do the same thing with pathogen genomes, only in this case, instead of a sentence, we're reading something that's the equivalent length of the book War and Peace, if we're doing a typical bacterial genome. And over the course of that entire outbreak, then you've got, 20 kids sitting in a line reading War and Peace to each other 20 times, only, 15, 20 letters in that entire book might change. But that's enough. That's enough for us to be able to figure out the order of transmission.
COVID has changed our world immensely. Our world of work is almost exclusively COVID-19. It's about the community transmission and how to stop the spread, bottom line.
More now on that breaking news about that highly transmissible COVID variant. It was only detected here in the United States today, but we're now learning the 2 South Carolina patients who had it were actually infected earlier this month. Here's CBS's Mo Alengi.
Tonight, South Carolina's governor is telling residents not to panic after 2 cases of the highly contagious COVID strain, first identified in South Africa, were detected in the state. South Carolina now ranked 2nd in the nation for new COVID cases per capita.
This virus has been matched by the speed of innovation.
There's been this really unprecedented, rapid response of all of these scientists all over the world, just sequencing the heck out of all of these viral genomes that they're getting and putting the data into a place where all these other scientists can access it.
No doubt that things are moving much faster than they ever were before. What used to take years is now taking months. What used to take months is now taking weeks or even days.
So we've been able to, within a few weeks of us learning about COVID, we can go into these databases and pull down like 100 genomes or 1,000 genomes of this virus.
The tools, the technologies, the approaches that we are known for in cancer are those that we also apply to the genome of this virus.
With genomics, one of our goals is to really carefully map out not just individual samples, but trying to map out all positive samples in Arizona.
We can look at the virus genomes and be able to determine who may be transmitting to whom within the greater population.
TGen North is the Pathogen Genomics Division. In Flagstaff, we're using those same tools and technology, but we focus on infectious disease, the microbes, the bacteria, the viruses, the fungi that cause some of the greatest problems around the world.
Everybody's heard of DNA fingerprinting. It's done in crime labs, right? We do something very similar to that with pathogens. We use the genetic material that we find in patients, and then we build databases that we search and identify the source.
We focus on viruses, bacteria, and fungi. Whether it's influenza or MRSA and other superbugs in our hospitals, or some of the really bad things like anthrax and plague, or valley fever right here in our backyard in Arizona, we're able to essentially advance the fields of clinical medicine and public health in ways that we didn't even think were possible 5 years ago.
Unique about the work that we do here at TGen outside of our clinical diagnostic laboratory is that we have the capacity to do whole genome sequencing on the virus. So samples that test positive in our laboratory and samples that test positive at the Arizona State Laboratory come to us, and we have an amazing sequencing team that does whole genome sequencing on each of the viruses.
We've been working with governments and with businesses and trying to give them the information that they can use to move forward in the safest way possible for either their constituents or their customers or their employees.
The question is, what haven't they done? They've done so much. They've been with us from day one doing the processing of specimens. They've given us volunteers to work the blitzes. They've given us supplies when we didn't have any. They work weekends. Their turnaround time is wonderful. There's nothing that they don't do.